Greetings, this is Stephen McKenzie. If you want to learn more about me, you can look at the About page on my YouTube channel, or I'll leave some links in the description. Link to this GitHub repository to show you MLibs. It's my embedded library that I've been working on for several years now. I've made some recent additions. And what is it? It's a collection of modular C-based libraries designed for embedded systems. I used to have C++ in it, but it was kind of duplicate, and it's better to just use the standard library. So I tried to provide a lot of the STL type functionality to contiguous memory types. And so what does it target? Well, for this, it targets the STM32 series. You could easily broaden its application. You don't need any exterior libraries. I have all the libraries. When you clone this project, you get all the libraries you need. The only thing you may need is a linker file specific to your board, but if it's a STM32 this will probably work for you. So what's the objective? It's to provide high performance and especially efficient data structures and algorithms for embedded environments. It's very memory aware. To provide a test automation for frameworks, automating embedded testing for validating embedded code. It's mostly, though, it's not so much for testing the board itself, but for data structures and algorithms that you want to use in a constrained environment with limited resources like a microcontroller. And so, as I said, I want to provide standard C++ library type of semantics, for embedded environment. So some of the key features is support for fixed size arrays based data structures, but also I do use a custom allocator that provides dynamic allocation semantics, but in reality it's a fixed array heap type implementation by Jonathan Valvano, a well-known embedded professor down at University of Texas. And so what are some of the things I use? I use the CMSys and HAL libraries for STM32 specific operations, but a lot of the it's all bare metal. I don't use a real-time OS. And so, as I said, I use this custom allocator. And so this is where you can get it on GitHub. My username is SteveMac321. And I'll have a link in the description. And I have a pretty good README here that shows you how to set it all up, how to run it. It's pretty straightforward. I've gotten it to work on FreeBSD, but it's mostly for Linux. So I'll go through a few more slides here, but we'll get down to showing the automation, how it works, and look at some of the code and do kind of a deep dive into the library. So maybe a multi-episode YouTube video. We'll see how it goes. So the architecture and testing framework. So the projects are modular. You can run them all at once, or you can use the individual data structures independently, and algorithms as well. I used to maintain a desktop version, but now I just keep it for one simple purpose for the microcontrollers, but you can use the code on a PC. It's nothing to prevent you from that. And I do use a generic function pointer based approach like qsort, voidstar. In a way, it tries to copy templates. That's the voidstar. In some ways, I wouldn't want to use it in a mission critical type situation where you want to be very careful about type safety. But I provide a lot of functors, and I have a whole functor library, so that if you use the tests the functors that I've provided that are well tested, you can have quote-unquote type safety. I wouldn't, it's kind of the anti-Rust pattern in a way, but C is very good language for embedded systems, I think. I do write some embedded Rust as well, but C is very ubiquitous in the embedded space, and even much more so than C++. So I have a test automation framework. You can build a project though by going to the project directory and building it, and you can run a private debugging session. A singular debugging session right there in the directory. But I have a Python script. Python script that you can build, clean, flash, run the tests from a central location, or run them all at once, or build them all at once, or clean them all at once, or do all three of those things in session, or just one, and so on. It's pretty versatile. And so it supports semi-hosting, which means you get feedback. It prints back to your console. And I'm using ST-Link and OpenOCD for the real-time feedback from the microcontroller. As far as a tool chain, it's ARM embedded, so it's the GCC ARM, either the GCC ARM None EABI or the multi-arch GDB, or GCC and GDB. But on Linux, all of that is supported. You can use Aptitude to install it, and it puts it on your path. So it's pretty straightforward setup. And then also, I've checked in some Doxygen files. I didn't check in all the docs that are generated, because that would be a lot of bloat, but I have instructions on how to build it. And we'll take a look at some of that visual representation of the libraries. So before I show you how to run the tests and how to build the tests, let's talk about what's going on. So, I'm building on a host, on a PC, and the microcontroller is hooked up to the PC with a USB port through a ST-Link interface. And anyway, what happens is it gets built into an ELF file. And ELF is going to contain full debugging information, but then we use GCC tools like OBJ copy, and we create a bin file, which is stripped of all the debugging. And so that smaller bin file is what gets flashed to the flash memory on the microcontroller. And then you have either ST-Link or OpenOCD to act as a proxy between the board has an onboard debugger, and so either ST-Link or OpenOCD acts as a proxy, reading the debug registers on the microcontroller. It acts as a proxy between that and the GDB server. However, when you load GDB with the program, you load the local ELF file on your system here, and so you get all the full debug symbols, and you get source file level debugging. And so the ST-Link or OpenOCD acts as a proxy between the two. So it depends on sourcing a env.sh, which sets up the root directory, and then all the make files depend on the variables that are being set there. And then you have a Python script that runs it. It cleans it, builds it, flashes it, and so on. And also you can navigate to a test directory and just type make, and it builds, and you can set up a debugging session. What you have to do in that case is start ST-Link or OpenOCD in a separate shell, and then run the debugger. And the reason you don't have to do that with the automation is that my Python script is starting multiple processes running at once. So you're running two processes. You're running the OpenOCD process, and you're running the GDB process all in one shell in the background. So here's the environment. You probably can't see it on the screen, so I'll explain it. I have a script called BFR build flash run, bfr.py. It's a Python utility. And so it automates the build. It creates the bin file, it flashes it, it runs it, and it will run everything from the root here if you want. You just say which test directory you want to build or clean or flash run. If you just choose the test directory at the root of that directory, it'll run all of them at whatever. Now I find it works best if you do a clean, then do a build, and do a flash run. Although you can say clean, build, flash run, and it works most of the time. I haven't tried it for a while, but anyway, here I'll go ahead and do the clean. Here's clean. Here's build. And then flash run. So it erases the board. It writes to the board, runs the program, and you'll see some red output, and just the shell itself, when it sees the word fail or no, it prints it red, but it's 0 failures. These are some, it's printing out some floats. So the test pass, and then here it just erase the board again, flash a new program, and now it's establishing the connection, and here now it's running it and outputting the test results through semi-hosting. The way I'm doing this is through a GDB script, so it's using the script to tell GDB what to do, and I have a dummy function when all the tests are done that it has a breakpoint and kills the process there, because the process will just keep running. So you have to kind of kill it. And so there's a lot of test cases, and the functors allow for that. This is graph output. Okay, and that's it. I just ran the suite. Okay, so if you want to debug one test, you go ahead and navigate to that test, and you can run make and build it. Of course, here I'll have to run clean first. And then you navigate to the debug, and you'll see that there's 2 files in there. There's a test.bin and a test.elf. So you're going to load test.elf into the debugger, and then you're going to flash test.bin onto the board. So we'll do that manually here. Use st flash and then erase. So now it's erasing what was currently on the board. Then you run st write testbin. That's what you're going to flash, and the starting address is 0x0800. 0000, and so it writes that, and then just st flash reset the board. It starts it over. So then here in my write shell, I'm going to start OpenOCD. So now it's listening on port 3333, and then over here I'm going to start GDB multi-arc with -TOI, so we get some source level looking debugging, and there it is. And you want to say target TAREXT:3333, and then I'm going to set a breakpoint in main and load. Then run, and so I get my breakpoint here in main, and then just regular GDB commands like N for next, and C for continue, and so on. So that's what it does. And you can also use stutil, but it's listening on port 4242, so you'd say target ext:4242. And so there you go. So anyway, let's do a deep dive into the classes themselves. So we'll start with the C algorithm. overview. It provides function-based sorting, searching, modifications. I have a functor library that provides you with what to put in these, like comparison operator here and so on, or a predicate, like count if it meets this predicate, or comparison here, or is sorted, all of, and so on. If there's any type of, here's transform, so it takes a functor that does something, modifies the the array basically. In general, it provides a comprehensive set of generic algorithms for modifying, manipulating, analyzing contiguous memory blocks, typically arrays. Uses function pointers to be generic, and it's highly adaptable and reusable for a wide range of scenarios. It's designed to be type agnostic, supporting operations in any element type, as long as the appropriate function pointers are provided, the functors or predicates, for comparison, transformation, modification, or visiting. So what are some of the services? There's sorting and searching. There's transformation and modification. There's non-modifying, like visit, count if, equal, is sorted, all of, any of, none of. Modifying algorithms, things like there's copy, replace if, reverse, swap ranges. There's numeric algorithms, accumulate, product, inner product. And they work seamlessly with other components that are in the functor library, which are very well tested. So you can use types like all types of integer, numeric types, strings, structs, and then some of the work seamlessly with the data structures in the library. And so some of the stuff's pretty self-explanatory. There's visit, just iterates over a block of memory and calls the provided function pointer. It's read-only, so it doesn't modify anything. There's transform and modify. These, again, the type of transformation or modification is done in the functor. There's sort and search. And so I have sort and search routines. All you have to do is provide the comparison, but I have comparison operators for almost all types. If you have a special record, I have a pattern called a student that you can use as a model to show how to compare records. There's count if, it counts elements in the block that satisfy a given predicate. There's equal, it compares two ranges for equality based on a comparison function. There's is sorted, it checks if an array or contiguous memory is sorted based on a predicate. There's copy, it copies elements from one block to another. Reverse copy, copies elements in reverse order. Swap ranges, swaps elements between two blocks. There's numeric algorithm, accumulate, computes the sum of elements in a range. Product computes the product of elements in a range. Inner product computes the inner product, sum of element-wise products of two ranges. And if you go to the Doxygen, here I'll show you what the Doxygen looks like. I have Doxygen that give you a full explanation of each element of the library. And so I'm kind of reading it. And so then there's examples of how to do it. And so then if you go in the Doxygen and go to the files, it gives you a file list, and this is algo.h, and it just shows some of the services here. These are the tests that test, sort, and transform and modify. Search test, a bit manipulation test, which I have a bit manipulation class. Deduce type, merge test, swap ranges, random shuffle test, count if, equal test, replace test, and so on. You can look at, get a visual representation. You can look at the code, implementation of the code. So let's look at visit. It's pretty straightforward. Here's the just has a pattern of the source being the first argument, the destination being the second, how big it is the third, and how big a particular element is for a lot of these. And then for a lot of these, it comes with a functor. And then if you look at the source code, you can see that have a lot of data here and a lot of tests that get run, a lot of support, a lot of functors built in. Next, we have an array class. It's a dynamic array, but it has resizing semantics like realloc, but again, we're using this custom allocator that is essentially a fixed sized array with that acts as a heap. Again, it was implemented by Jonathan Valvano, Professor Valvano. So you get the safety of array, but you get the allocation semantics. And so they're not quite as tightly coupled with the algorithms as the STL is. The difference is that these classes, they will wrap the algorithm. And I'll show you. So for example, array sort. So here's array sort, and it basically calls the generic sort routine. And has many of the same patterns as the algorithm library. You know, array search, array transform, array modify, and so on. It's one of the limitations of not having templates like in C++ is that it's not as tightly coupled as the STL, but they are coupled somewhat in that they wrap the algorithms. Now here's an overview of the functor and generic operations. Uses predicates as for swapping, for comparison, for printing, for transformations or modifications. So here we have bool, int less, int compare, string less, string compare, record. And so it shows you here a pattern for a record. A bunch of print types: print integer, print hex, print string, print pointer to a string, print student, which is a pattern for printing a record. Transformation functions, double int, and then this one's very useful, rand int. So you can get a random, and then you can get a generic random that you specialize in your implementation of it. And here's an example, but you can look at the test code. Here's all the explanations. They have a bit vector class that's an inline. You can just include it. And it has all your regular bitwise operations: bit set, lookup, print, bit count, bit set, is set, bit, and so on. And here's all of that, and have lots of tests for that. I have this custom heap allocator. If you want to look at it, the source file comes with it. It's heap malloc and heap free is all you really need to know as a user of it. Now it's not STL compliant, like you can't plug it into a std vector. I do have a std vector compliant allocator in some of my other projects, not in this automation project, that do work with the C standard library if you want to plug in a custom allocator and use a fixed array allocator that supports dynamic allocation semantics. That's in this other project on my GitHub just called Embedded. And if you look in main.cpp, you'll see void test placement STL. And so here's how you declare it. So I'll make this print bigger. So you just instantiate a vector, and this one's int, with this static allocator int type. And I've got this class from Christopher Cormagnos. He has a book called Real Time C++. And I apologize for not having a link to. He has this up on GitHub. It's distributed under the Boost software license. It has a few files. I would say it works pretty well for most of the basic things you're going to want to do a std vector. It's not going to pass conformance tests though, but it's pretty good. So I also have an ARM assembly library with some basic things: copy, is equal, spin lock, transform. But the one that is most interesting is the sort. It's not a great sort, it's insertion sort. But if you have some arrays that are mostly sorted, it performs better than quick sort when the data is mostly sorted. Let's say you have 100 arrays you need to sort, and 90% of them are sorted. You're going to do better with insertion sort than with qsort. But mostly it's a academic exercise. What I did is I started with a C implementation of insertion sort, and then I just reasoned it out. And so I have a lot of comments here. I also have a video on my YouTube channel called MLibs where I walk you through this somewhat. But the comments are very good. And what's very interesting is using the left shift to walk the elements. And this uses the qsort pattern in that it will sort any type because it sorts the size of a pointer. Okay, so I have tests that sort integers, strings, matrix. It can sort a matrix because you can treat a matrix like a one-dimensional array. It's from the start to the end. Yeah, down here at the bottom, I just sort of show you how the shifting works to walk through the array. So another feature of the test is I use the lists from Linux and FreeBSD, the macros for all the, I just use list. They have all kinds, Linux has tons. They have splay trees and just all types of macro-based linked lists and so on. So I don't actually have any tests for it. I have it up there if you want to use it though. But here's an example how you use it. And you'll see these list macros all throughout the kernel. I've especially studied the FreeBSD kernel. So basically, if you see list head in a structure, like the process structure in Linux or FreeBSD, the list head converts a structure into a container, okay? And then if you see list entry, that converts a structure into a linked node. And most of the structures are both a container and a linked node. So one of my later additions that I've done recently is a priority queue. And it uses a detachable buffer. So you want to be on a microcontroller, especially one that, some of the newer ones have quite a bit of memory, but like a STM32 F4 or a 3, you want to be careful about, allocating a bunch of buffers. And so I reuse the buffers. And so I have a priority queue that you construct from an already allocated array. And it performs a max heap, the max heap property. And if you want to see it used in a more interesting project, this CMSys DSP, I basically I sample the microcontroller using analog to digital, and I capture those readings and run them through a fast. Well, first I have to create an array of complex numbers and run it through fast Fourier transform, and then get the magnitudes, and then I feed the magnitudes. I take that array created by getting the magnitudes and attach it to the priority queue, and then it run max heapify, and so then it creates the heap property, the max heap property on that array. And then I feed that into a graph that I associate, add edges to the graph based on the peaks and valleys. And so also the graph is in the library as well. We'll go to that next. Again, that's cmsys-dsp. You get both the priority queue, the graph, and how to get voltage. I have other projects that get temperature. I don't remember which one it is. All of this is pretty straightforward. So then here's the graph header. I have this enum with white, gray, black for the breadth first search. And then a vertex here that I have set to a float. So this I'm not using the generic patterns because I have a different philosophy today. When I first started developing this library some years back, it was the days of being on the Microsoft C++ team wasn't too far in my rearview mirror, and I was the tester for the STL, for the C++ standard library for ISO conformance. And so I enjoyed implementing std vector to the ISO standards, my own, and I don't have that in here because that's just my own, for my own fun and education. But I was very much influenced by Mike Acton. He's a game developer, pretty well known in the game circles. At the time, he was Insomniac Games. Is that a company? He really chastened the C++ community at CPPCon 2014. It was kind of a well-known talk, and he really stressed data-driven development instead of the sort of object-oriented. And it influenced me. And so as an embedded developer today, which I'm not an embedded developer, but when I do target these devices, I do think less about generic and code reuse and think more about that the hardware is the platform and less about code reuse. And I'm thinking more about type safety as well. And so I do get into Rust embedded development too. But so this is still C. And I do have a lot of C++ embedded stuff, but this library is purely C. The point is that I specialize. I don't specialize anymore. I pick a type. And if anything, I might use a type def to make it somewhat generic. You just change the type def. But I'm using float here for this graph. So float is the main data. And so then, I create an array of vertexes. And then also, instead of having the edges being like an array of integers, I do save space by making it a bit vector. So again, I'm being very careful with buffers and space and all of that. So the nicest data structure in my library, this is something else I added lately, and that's a open address hash table. Now I used to have this with that void star implementation with the dynamic allocation semantics using the custom allocator, but I changed the value semantics like the STL and like Rust. And so the problem with value semantics on an open address hash table is when you populate a bucket with a value, how do you represent an empty bucket? You can't say 0 because 0 is a valid entry. And so I use a parallel bit vector. And that's what Rust does as well, is my understanding. And so one of the nice features of this table is that I offer a lot of analysis. So first of all, I have some analysis that just gives you a visual view of the table. And so I have a 50% load balance. So if it's if it's 1028 buckets, then I fill it with 512 or something like that. And so the blanks are empty, the F is full, and you get a representation of how the distribution is, how many clusters there are, and if I'm getting a lot of collisions. So I have that. There are a lot of collisions. There's 400 or 514 occupied buckets, 232 collisions, 0 duplicates. There's 229 clusters, a total of 514 cluster length. The average cluster size is 17, but the average cluster length is 2.24, which is pretty good. Not going to complain about that. So I use double hashing and a quadratic probe to kind of leap the thing around to find an open bucket. Like I said, it has value semantics, has support for floating point types. I provide the cluster analysis and statistics. I have it's not full interface. It basically has insert and lookup, and that's about it. The way you set the size, I think, is with a define in the compiler line. A -D. Anyway, and they have is slot occupied and so on. But I'm pretty happy with this data structure and how well it performs. And then finally, the last thing is, I was always suspicious that there was a hole in random number testing about the randomness. And so, I don't want to kiss and tell because I worked on the team, but it was tested like maybe once, and it's probably still good. So I wanted to test the random number generator in the embedded library. The nano-newlib comes with STM libraries, and it passed. And so I do it's the chi-square or chi-square, the Greek for x, chi, I think that's what it is, chi-square. You can read about it here. I have the formula in there. I got the algorithm from an old Sedgwick book. It was Sedgwick Algorithm C++, 1992. It was the very first Sedgwick book I bought. And there's still a lot of things in there that his newer books don't have. So here's the code, and here's the formula. You can read more about it in my Doxygen. Anyway, so the test passes. So I have 10,000 number of random samples and 16 number of bins. And so it fills up these bins. And then this result, you compare it against R and against this formula here. Basically, that chi-squared is equal to sigma I equals 0 to R F sub I minus N, which is the size of the array, divided by R squared, and this whole formula is squared, divided by N over R is the formula. And so that's sort of the direction I want to head with a lot of this. I want to get into more of the standard numeric libraries and see how many of them are offered in the embedded libraries. Kind of transition over to C++. And also, if you want to get into Rust embedded, I forked this repository from the Rust embedded books GitHub, Rust embedded Cortex-M quick start. And the only thing I've added was specific instructions for the STM32 F401RE, basically all the STM4s. And I give you step by step how to get the tool chain, how to get which one to get for the board with the floating point support, getting the ST-Link tools, and how to set up your linker file, since they split the linker file between what you have in your project and then they generate a generic one further down towards the binary in the tree. Then you have to add some dependencies and package information in your cargo.toml. And then this is your main, which using no standard library. So this is bare metal Rust. And then I use how to build, and then I do the manual flash write and reset. And then I do the 2-terminal debugging session like I showed you before. And if you enter these commands and so on, and you can check your binary size and so on. And I have some resources here. So that gets you started with Rust embedded. So I'll close with this Doxygen document that you can look at the files, you can look at the classes, you can look at topics. These related pages is where all the detailed instructions on each class and algorithm is at. Anyway, I think that's about it. So hope you found that helpful. Hope you'll clone it and contribute. If you want to give me feedback, do it in the form of issues on the GitHub. And so anyway, thanks for your attention.